Welcome viewers to the 16th lecture on non-traditional abrasive machining processes, and we have already covered ultrasonic machining and abrasive jet machining, and today we are going to take up abrasive water jet machining. In abrasive water jet machining, first we have to talk about water jet machining, what it is, and after that we will be talking about abrasive water jet machining. Water jet machining means that just like we were using pressurized gas in case of abrasive jet machining, we will be using water under pressure and allow it to expand into allow it to convert the pressure energy, that is the pressure head, to velocity or kinetic energy, velocity head, and that way get a tremendously high speed of a jet of water emanating out of a nozzle. Now, what can we do with this jet of water at high speed? Can we cut thick metal pieces? Not exactly. With only water, we have to restrict ourselves to the machining of materials like say wood, leather, frozen meat, etc., etc., and metal foils also can be machined with water jet machining equipment. Now, how much will be the speed of this water jet? It will be roughly around 1000 meters per second, that means 1 kilometer in 1 second. That is quite an impressive speed. And what is the pressure generally that will be applied in order to get this particular attain this particular speed range? This will be around say 4000 bars, 4000 bars. So, in order to achieve such a velocity head, what we will be doing is we will be first of all attaining a very high pressure, and after that, so first of all comes the question that how do we attain this pressure, but before that just a few sentences in by way of introduction. Abrasive water jet machining stands out among all the non-traditional abrasive machining processes. In what way? Abrasive water jet machining can machine almost all materials, while ultrasonic machining and abrasive jet machining, they are rather restricted in their application to glasses, ceramics, brittle materials which are generally non-conducting, etc. But for abrasive water jet machining, just anything can be machined, and the added advantage, the plus point, is that it leaves behind no thermal effects. What do we mean by thermal effects? If we are using say wire electrical discharge machining or laser beam machining or oxygen cutting, etc., in all these cases we will have quite a bit of thermal effects in the cut material. In what way? The laser will be using very concentrated high energy density beam, so that a large fraction of it will be absorbed by the workpiece, which will be reaching quite high temperatures, and for that a lot of thermal effects might be seen in the workpiece. In gas cutting also we are having a burning of acetylene, so that say in case of mild steel we form oxides which are liquid at a lower temperature than that of the melting temperature of the material, so that the oxide is created and it flows off due to gas pressure, and that way cutting is achieved. So, naturally a very high temperature is attained there, and there also there will be thermal effects. Thermal effects can be detrimental because it can change the properties locally near the cut, while the basic material has different properties. Okay. And wire electrical discharge machining can produce temperatures which are to the tune of thousands of degrees Celsius, and quite obviously we are going to have some thermal effects. So, thermal effects are quite detrimental in the sense that they produce property differences with the basic material, and it is really a very big advantage that we will have almost no thermal effects out of abrasive water jet machining, because the water itself serves as the coolant. Okay. While we are cutting, we are cooling. So, we will be employing water to cut metals, rocks and stones, which is quite unique, this idea. Of course, we are using abrasives along with water, but it makes abrasive water jet machining quite a unique tool. So, as we discussed, the water is going to be taken up to a pressure of around 4000 bars, and from there it will be emanating from a nozzle and attaining 1000 meters per second or so. And if it is if abrasives are put inside, the velocity will be slightly less, but still of the same order. Okay. So, what can be why should we look for abrasive water jet machining or abrasive jet machining? In what way can we have its applications? I can name one or two applications on the higher end. So, that is, say for example, when we are thinking of rapid prototyping with first order approximation. Now, what do we mean by that? Let's have a quick look. If you look at this particular drawing, suppose I am doing rapid prototyping by cutting out laminates, that means layers of material, and then I am sticking them together. Okay. In what case would I be doing it? I might be doing it for layers of material. Let me draw an example. Suppose this is the particular body that I want to develop. So, I will be cutting it into layers. I mean, I will make a CAD model and I will cut it into layers, and then I will be forming. I will be trying to physically realize these layers and stick them together and get this job. So, this is virtual CAD model. I will slice it. So, sliced CAD model. These slices I now try to realize physically. How can I do it? Generally, when they are realized, they come with an approximation. What is that? That is called zero order approximation. Some cutter has been used to cut this out of a sheet of material or a plate of material. It looks like this. Now, you can immediately point out two defects here. One is that these are straight cuts, okay, that really cannot be avoided in case of CNC technology. Straight cuts, most of them. Okay. You might be able to what do you call it, might be able to remove some of them by curvilinear paths if they match, okay, but some sort of approximation has to be tolerated. But yet another tolerance which we are perceiving here, which we are seeing here, is that these walls are vertical while these walls are inclined, okay, inclined and curved, and these are straight and vertical. Okay. If we have a 5-axis water jet cutter, in that case we can develop something of this type. These will still perhaps be straight, but these can be inclined. So, water jet cutting will allow us to cut this sort of a layer in which we are simply using a 5-axis water jet cutter. Of course, in the same way we can use other cutting heads like laser cutter, okay. And if technology is good enough, we can use a wire EDM also. But these cutting technologies, abrasive water jet cutting, proves to be a very good member in this particular group. So, in the same way, profiled edge lamination tooling we can also employ a water jet cutting device in order to realize these layers. So, this is by way of application. There are other applications also. We will be going through a detailed discussion on the applications later on. Let us have a look at the machine. What does the machine consist of? First of all, it is understood that we have to develop a very high pressure of water. 4,000 bars is really not a very low pressure indeed. So, we pump and intensify the water to a very high pressure. How we do it, we are going to come in the next slide, but let us first try to understand the overall idea. Once we have developed the pressure, we accumulate the water at a very high pressure to remove pulsations and pulsations in the pressure. That means, if we are using say a reciprocating device, this reciprocating device will develop the pressure, recede, develop the pressure, so on and so forth. So, that there will be pulses of high pressure in the supply line. In order to remove that, just like a flywheel removes surges in energy. So, in the same way, we can get the water to accumulate at high pressure in a reservoir, which will be removing such pulsations in pressure. After sufficient pressure has been developed, we can let it out through a very small orifice here. This orifice allows the water to come out, okay, at this particular point. What sort of diameter are we talking about? We are talking about a diameter of say 0.2 to 0.4 millimeters. 0.2 to 0.4 millimeters, that means 200 microns to 400 microns. Such a small orifice built drilled into say some jewel, that means a very hard stone. So, through that particular orifice, water is allowed to the pressure is released, and for all practical purposes we can assume that it comes out into atmospheric pressure. So, that the whole pressure head gets converted to velocity head. Mixing chamber means at the mixing chamber, abrasives are entering into the water stream. Why so? Because of the different types of water jet or abrasive water jet machines available, we are here looking at the entrainment type. That means, the abrasives are drawn into the water line at the mixing chamber. Okay. So, they are not pre-mixed, but they get mixed up in the mixing chamber. So, in the mixing chamber what happens? A sort of vacuum is created. Vacuum is created by the ratio of the diameters of the orifice and the focusing tube. So, that a partial vacuum is created, so that the abrasives are entrained or drawn into the mixing chamber by this suction into vacuum, and they have to pass through this abrasives and the water, they have to pass through together through this focusing tube, where gradually the abrasives take up the they are accelerated to the final outgoing velocity of the combined jet, and when it comes out, the abrasives have reached the same velocity as that of the water coming out at the exit of the focusing tube. Okay. So, essentially we are having abrasives coming in as the focusing tube is uh, releasing the water into the atmosphere. Atmospheric pressure is existing there, and as in the mixing chamber, through the orifice, water is coming out through a very small diameter, and abrasives are getting drawn into the particular stream of water, and therefore mixing is taking place, and finally completely it is taking up the energy in the focusing tube, the abrasives, and ultimately it is coming out together. So, when this particular water is initially it has to be pressurized, this sort of a device is used. What is this? Water is here in this small confined chamber. At present its pressure is not very high, but pressure can be built up by this device. What is this device? There is a large piston here, and this large piston is connected to a rod. This shaft connects up these two cylinders. This cylinder piston cross section area is very small, and their ratios might be 50:1, 40:1, like that. So, suppose this sectional area is 50 times that of this particular section. Water is filled inside, and say at 100 bars pressure, this piston is applying, we apply pressure on this side, so that this piston is getting pushed towards this side. So, if there is 100 bar pressure multiplied with the area, let us call it E1. Okay, E1 into 100 bar will give us the force with which this piston is getting pushed. So, it transmits that force towards this side, and again this force is applied on this particular piston on this side. So, when the pressure is being created at this end, the force which was developed, it gets divided by a much smaller area, 50 times less, and therefore, the force which was developed here, the pressure which was developed here, ultimately it gives rise to a much higher pressure, 50 times higher pressure, due to this area difference. Why? Because 100 into E1 divided by E2 is equal to 100 into E1 by E2, which is 50. So, 50 into 100 occurs here. Okay? Much higher pressure is created here by this simple system. And if we look at the full picture, let us now have a look at the basic schematic of the supply of high pressure water. So, first of all, hydraulic power pack with a direction control valve, it is responsible for putting in pressure at the high pressure water, that means which is coming out of the hydraulic power pack, say at 100 bars, it is coming here, and the same thing that we saw here, with the difference is that once it presses to this side, and on the return stroke it presses upon this side, and there are two similar cylinders on the two sides, and the power, the water which is at very high pressure now, that is delivered to a central reservoir called the accumulator. So, that it is not just pulses of high pressure occurring at regular intervals in time. No, roughly we have more or less uniform pressure being developed with respect to time. Once the stroke is taking place on this side, so we are having a pressure surge, increase in pressure and supply to the accumulator at high pressure. We are having the return stroke occurring this way, when the direction control valve has shifted the supply and the discharge to the sump. When it has switched them, then this starts moving towards the right hand side, and water supply takes place at high pressure from this point. So, this way we are removing the effect of surges or pulsations in the high pressure which is being developed, and from the accumulator ultimately this water is sent towards the mixing chamber, if you remember. So, from here we are going to the mixing chamber. So, as we discussed, the high pressure head of the water so developed is ultimately converted to velocity head. This is done by passing the water through an orifice, etc., etc. We have discussed these things. So, let us look quickly at the conversion. That means, velocity which can be developed is calculated this way: v square is equal to 2 p by rho. Why? Because from Bernoulli's equation, if we have a quick look at the calculation, let us see. We have p by gamma plus v square by 2 g plus h, velocity head, pressure head, and this is the height. Okay. So, this one will be equal to, if we take another position, p 2 by gamma v 2 square by 2 g plus h 2. We start from a place where there is absolutely no velocity, no height, same height as the previous one. So, in that case it is called stagnation. Okay. The water is starting from stagnation and only the pressure head will be existing. So, in this case such a thing is happening when the accumulator is letting out the water for expanding to atmospheric pressure. So, in that case we have p by gamma, where p is equal to that high pressure, that is equal to v square by 2 g. P 1 by gamma is equal to v 2 square by 2 g. What is this? Atmospheric, the velocity that is obtained when the water comes out at atmospheric pressure. What about the other terms? In the atmospheric pressure, we are considering gauge pressure to be 0. So, this one, okay, is the velocity that we are going to get, and that is what we have written here. Let us look at this. V square by 2 g is equal to p by gamma, and therefore, if we remove the g from the expression, we have v square is equal to 2 p by rho. Okay. So, this thing we have already discussed. So, I am skipping this one. Yeah. So, let's quickly have a look at the calculations. What does it read? It is a problem in case of water jet machining. What is the velocity of water that would emanate from a tank at 4050 bar pressure? The outlet diameter of the nozzle is 0.3 millimeters. The density of water is 1000 kg per meter cube. 1 bar is 10 to the power 5 pascals. Okay. 1 bar is given to be 10 to the power 5 pascals. So, we start with our original expression. What was that? P by gamma is equal to v square by 2 g, or v square is equal to 2 p by rho. So, once we put in the values, we are going to get an estimate of the velocity. Mind you, up till this moment we have not put any abrasives inside the water stream. So, let us see what we have done. First of all, the pressure is 4050, and we have converted it to pascals. So, we have 10 to the power 5 here divided by the density of water, that is 1000 kg per meter cube, and after calculation the velocity of water is coming out to be 900 meters per second. 900 meters per second. Okay. So, with this velocity of water, you can do a lot of cutting, and I'll just give you a corollary of this. That is, suppose you are standing at the basement of the tallest building in the world, and you have come as a representative of a water jet machine selling company, and you want to demonstrate, you have come with the intention of demonstrating the work of a water jet machine, and then you find that the consignment bringing your equipment, it has not arrived from the airport due to some some confusion. So, at that moment you decide that in order to give a demonstration of water jet machining, you will use tap water, and the tank is at the top floor. Say it's a very tall building, say Burj Khalifa, okay, in the Middle East. It is most probably around 900 meters high, if I am not wrong. Hopefully, I am correct. So, if you use tap water with the tank at the top floor, then find out whether you are going to attain the velocity in the range of typical water jet machining velocity, so that you can go on with the demonstration. Find out. Let me anyway continue with, since I have a few minutes, I can continue with 1 or 2 points from the next lecture. So, that particular problem you can find it out, most probably it will come around, speed will come around. So, first of all, it is your duty to find out the height of the building. I do not remember it, it might be 848 meters, or I think so, 848 meters. So, you can put V square by 2 g is equal to h1, and therefore, V square is equal to 2 g h, and from that your velocity will be coming out. Okay. And in fact, we can have a quick try at calculating it ourselves. Give me one moment. So, let us have a, do we have Excel here? Let us see quickly. That is right. So, let us try out the calculations ourselves and see what sort of results we are getting. So, this is equal to V square is equal to 2 g h, that is good. So, this is equal to root over square root of 2 multiplied by 10 multiplied by, let us make it 900, sorry, and the velocity is only 134. So, therefore, it is absolutely impossible to demonstrate the effect of, demonstrate the working of water jet machining using tap water at the ground floor of the tallest skyscraper in the world. You have to have some pressurizing equipment. And also, we have not considered the tremendous amount of losses which will occur due to flow of water from the top floor through pipes up till the ground floor. That will take half of your energy away, so that you cannot really carry out machining with tap water in any case. Okay. So, let us go back to the, yes, we will just have a quick look at this and then stop. Discharge volume. Now, discharge volume means what? Since we are having water emanating at a particular velocity, we can also estimate the discharge. The discharge is equal to simply velocity into cross sectional area into the discharge coefficient. Okay. So, this is the discharge coefficient, and this one is the cross sectional area, and this is velocity. It can be expressed in pressure head, and therefore, we can have very simple numerical problems based on these. Okay. So, let us stop here, and we will continue in the next lecture. Thank you very much.